this can be given as the sum xi from 1 to n is equals to n x bar. Okay. So what is this class? What is this? Yes. What does this mean? N times x bar. What will it give us? N is the sample size, isn't it? Yes.
Yes.
X bar is the sample mean. So when you multiply the sample mean by the sample size by the sample mean, what do you get? You get the sum of xi's, isn't it? Okay. So this xi's, what does that mean? That's complete enumeration. That's complete enumeration of all the units in a given sample space. What we have in the denominator here, x1 plus x2 plus x3 up to xn. You understand? Yes? So is that the same as the total? That's the same as the total, isn't it?
Yes.
Yeah, so that's what we mean by the total. That's the sum of all the observed values in that sample space. Is that clear? So because we are saying here, we want to define the sample mean and the total of all those values observed. So that is what we have. So we define that by using capital T, that's the total of all these values. We call it the complete enumeration of all the units in a given sample. So let's look at what we mean by a central limit theorem. So CLT, that central limit theorem, states that the sample mean x bar follows approximately the normal distribution with mean mu and standard deviation given by sigma divided by the square root of n, where mu and sigma are the mean and standard deviation of the population from where the sample was selected or from where the sample was drawn. Okay. So it follows approximately the normal distribution. So, you know, the normal random variable x is denoted by, we say x follows normal distribution with mean mu and standard deviation sigma. Here we are talking about the sample mean, the distribution of the sample mean. So we're saying x bar approximately follows a normal distribution with mean mu and standard deviation given by sigma by the square root of sigma by the square root of n. That is what we are saying. So you remember how to standardize the normal random variable to get the standard normal. You remember that? Yes. If x is a normal random variable with mean mu and variance or standard deviation sigma, then we have, this is the normal random variable. Okay. Then here we have the standard normal random variable, that is z. So how did we standardize this? We say z is equals to x minus mu, this x here, okay, minus mu, what we have here. So x minus mu divided by sigma. So this one approximately follows normal distribution with mean 0 and standard deviation or variance equals to 1. Okay. So is that okay?
Yes.
Yeah. So we have what's happening with my stylus pen here. Oh yes, the car is down here. I'm looking for this one. was looking for this guy. So let me erase this. I can write this properly. Okay, so that is x. So again, we are saying the sample mean x bar is approximately normally distributed with mean mu and standard deviation given by sigma by the square root of n, or variance given by sigma squared divided by n. So how do we standardize this? How do we standardize that? We say x bar, what we have here, okay, minus what we have here, that is mu. X bar minus mu. You understand? Yes?
Yes.
Divided by the standard deviation given by sigma divided by the square root of n. So this one approximately follows the normal distribution with mean 0 and variance or standard deviation 1. So another way is to, if you can simplify that denominator, then you rationalize. So you have square root of n into x bar minus mu divided by sigma. That's when you divide. So x bar minus mu divided by sigma over the square root of n. So x bar minus mu times square root of n by sigma. That's when you simplify. Okay. So that is the standard normal random variable corresponding to the sample, corresponding to the sample mean. That's what the central limit theorem is telling us. So the sample size n has to be large, and how large is large? When n is greater than or equals to 30, but in some quarters you'll come across n being greater than or equals to 20 for us to say n is large, so it depends. Okay, so the sample size n has to be large, n greater than or equals to 30 if the population from where the sample is taken is not normal. Okay, so that it allows us to generalize that this distribution is normal, then n has to be large. Otherwise, the normality condition may not apply. So when n is greater than or equals to 30, then the following statements are approximately correct, regardless of the shape of the population. So number one, x bar, that's the sample mean, approximately follows normal distribution with mean mu, standard deviation, sigma, divided by the square root of n, excuse me, okay? Then the total approximately follows normal distribution with mean n mu and standard deviation given by sigma times the square root of n. So you remember the total was obtained by saying x1 plus x2 plus up to plus xn, okay, which is equals to the sum of xi's, I from 1 to n. So this one can also be given by n times x bar, okay, n times x bar. So we're saying the normal distribution, I mean the total of n observed values from a given sample where n is large is approximately normal with mean n mu times sigma by the square root of n. Okay, so you remember x bar, what x bar is. So x bar, you can say x bar is given by t divided by n, because this gives us the total of the observed values. So make x bar the subject of the formula. So the sample mean is given by the total, where t is given by sum of xi's, then we divide by n. Okay, so how do you standardize this? How do you standardize that? X bar follows normal distribution with mean mu, standard deviation sigma by the square root of n. So when you multiply this by n, then you get n mu, what we have here. Sigma by the square root of n times n. What do you get? Sigma divided by the square root of n times n. So that's to say sigma by n raised to a half times n. So this is sigma times n raised to 1 minus a half. 1 minus a half is a half, isn't it? So sigma times n to power half. So power half is simply square root of n. You understand? Yes?
Yes.
Yeah, that is where we are getting, that's where we are getting this sigma times the square root of n here, and n mu. So this one, this is a standard normal random variable. So you see standard normal random variables, we say they approximately follow a normal distribution. This one follows approximately normal distribution with mean 0 and standard deviation 1. That's after standardizing. After standardizing. Okay. So I think that's okay. So let's see what we have next. So an example here, okay, so we are saying let x be a random variable with mean mu is equals to 10 and standard deviation sigma is equals to 4. A sample of size 100 is obtained from this population. Find the probability that the same mean, that's the sample mean of these 100 observations is less than 9. So we want to find the probability that x is less than 9. The sample mean. So x bar, the probability that x bar is less than 9. Okay. So what are we going to do? We are going to standardize. Okay. So how do you standardize sample mean? Sample mean is approximately normally distributed with mean mu, standard deviation sigma by the square root of n. So how do you standardize? Z is given by x bar, okay, what we want to standardize here, minus the mean, mu, divided by the standard deviation, sigma by the square root of n. So we're going to standardize the sample mean here, we standardize the value given here. So this will give us probability that x bar, okay, minus mu divided by sigma by the square root of n is less than 9 minus mu divided by sigma by the square root of n. That is what we want to do. So again, you remember we are standardizing so that we can use the standard normal tables. So what is this class? What is this?
Z.
Yes, correct. That is Z. So if we can go here. So that's to say, what is the probability that Z is less than, so mu is given, mu is 10, standard deviation is 4, and n is 100. This is n, okay? So we have 9 minus 10 divided by sigma, which is 4 divided by the square root of n, which is 100, like this. You understand? Yes? So that's to say the probability that Z is less than square root of 100 is 10. So you have 10 into 9 minus 10 divided by 4, like that. So that's probability that Z is less than 10 minus negative 10 divided by 4. That's negative 2.5. Okay. So you look at the standard normal tables, we want to get the probability corresponding to Z is equals to negative 2.5. Okay. So what is that value from the standard normal tables? Can you open your standard normal tables?
Zero point 0.062.
0.062. Yeah, so probability that x bar is less than 9 is equal to 0.062 or 0.62. Did I hear this? Okay, so I believe you've given us the correct answer from.
It's 0.00.
Oh, okay, thank you. Like this. So that is the value we can obtain from the standard normal tables. So similarly, we can say that the central limit theorem states that the sum, that is T, follows approximately normal distribution, okay, where mu and sigma are the mean and standard deviations of the population from where the sample was selected. So you standardize the total so that we have what we have here, okay? Because if this is what T is and we want to standardize, okay, then you say Z is equals to what we want to standardize, which is T minus N mu. That's the mean divided by the standard deviation of the totals given by sigma times the square root of n. So again, this is standard normal, which means 0, standard deviation 1. So let's see how to implement the second statement of the central limit theorem, looking at this example here. So let x be a random variable with mean mu and sigma, that standard deviation equals to 4. A sample of size 100 is taken from this population. Find the probability that the sum of these 100 observations is less than 900, okay? We want to find the probability that the sum. So sum here means the total, isn't it? The sum of the 100 observations. You understand? Yes? Then again, n is given by n is equals to 100. We're given the mean, we're given the standard deviation. So this is how we standardize, okay? So, but the question we want to solve here is to find the probability that the total is less than 900. So we standardize every value here. So that means we want to find the probability that T minus N mu, okay, divided by sigma times the square root of N is less than 900 minus N mu, okay, divided by sigma times the square root of N, okay. So what is this? Yes, this Z, what we have here, isn't it?
Yes.
Yeah, so we want to find the probability that Z is less than 900 minus N is 100. So 100 times mu. Mu is 10, like this, okay? Divided by sigma, which is 4 times, that's 4 times the square root of N, which is 100. So this is probability that Z is less than 900 minus 1000, that's negative 100, isn't it? Divided by square root of 100 is 10, 10 times 4 is 40, okay? So what do you get? That's probability that Z is less than, is it negative 2.5?
Yes.
Yes? Yeah, which will give us the same value, isn't it? 0.0062, okay? What we got from example 1. So this is just another way of defining what the central limit theorem is. That's why we are saying here, similarly, the CLT can be stated as follows, okay? So that's one way of doing it. So this question is no different from the one we did in example 1, simply to give us another way of defining the central limit theorem. So you can look at these other examples. The most important thing here is for you to know what the central limit theorem states. So follow these examples, then you can do this question here at your own time. So now I want us to look at the moment generating function for the normal random variable. Okay, let me see if I can access the LaTeX file for that. Yes. Yeah, the moment generating function for the normal distribution like this. Are you on this page with me? Yes?
Yes.
Yeah, so you know, this is a continuous random variable. So let me share my whiteboard here. Okay. So the moment generating function for a continuous random variable given by exponent of tx is equals to the integral from the lower limit to the upper limit, exponent of tx times the probability density function of x with respect to x. So this is the general definition of the MGF for a continuous random variable. So what only changes is the PDF for that random variable x. Okay, so this is equals to, for the normal distribution, the integral from minus infinity to infinity. You remember the parameters mu and sigma are defined between negative infinity and positive infinity. So exponent exponent of dx, or you write down the PDF 1 divided by sigma times the square root of 2 pi exponent of negative 1 over 2 sigma squared, okay, into x minus mu squared, okay. So this is the PDF of the normal distribution. Then you multiply by the exponent of tx. Then you integrate with respect to x, okay. This is what we have here, okay. Then f of x is the f of x for the normal probability or for the normal random variable, okay, what we have there. So we can simplify this. You can see here we have exponent of this term, then we have exponent of dx here. When you have a to power x times a to power y times a to power y, that's the same as a to power x plus y. Yes?
Yes.
Okay, then number 2, we have the square root of 2 pi sigma squared. Is this the same as the square root of 2 pi times the square root of sigma squared? So which is the same as, what's the square root of sigma squared? Is it sigma? Then times the square root of 2 pi. So this one is equals to this, isn't it? Yeah, so that the PDF for the normal distribution remains unchanged, okay? So we have the integral from minus infinity to infinity, okay? 1 divided by sigma times the square root of 2 pi, okay? Times exponent of negative 1 over 2 sigma squared, okay? Into x minus mu squared. This is the PDF of the normal random variable, okay? Then plus tx, okay, plus tx, what we have here. So the bases are the same here, so we are adding the powers. Then the integration is carried out with respect to x, okay. So we can deal with this chi first, the power of this exponent. We can simplify the power of the exponent to make our computations manageable. So we say, but negative 1 over 2 sigma squared x minus mu squared plus dx is given by, we can simplify this by completing the squares or by expanding this. So we have negative 1 over 2 sigma squared, okay, into x squared minus 2x mu plus mu squared. This is a quadratic function. When you expand that, we get this, okay? Then we can say plus dx. Is that correct expansion of this? Yes.
Yes.
Okay. So from there we have that's negative 1/2 sigma squared. That's from here. Okay. Into x squared minus 2x mu. Okay. We can rearrange plus mu squared minus 2 sigma squared t of x. So we're bringing this term outside the brackets, inside the brackets. So you see the terms inside the brackets have a common denominator of 2 sigma squared. So you can multiply this. When you cross multiply, you have 2 sigma squared t of x, then divided by the same denominator. So actually this one, 2 sigma squared and 2 sigma squared cancels. And we remain with what we have here, because this is a minus times a minus, which is a plus when you take it outside the bracket. So there is no change in the value. So we can rearrange so that we have -1/2 sigma squared into x squared minus 2x mu, 2x mu. Bring this guy here, so you have 2 sigma squared tx, then plus mu squared, like that. Okay. So we want to see if we can complete the squares. I believe you still remember what we mean by that. Okay. So that we say that will give us, we're moving from this point up there. So we have negative 1/2 sigma squared, okay, into x squared minus, what is common between these two terms here? What is common between this term and this one? Is it easy to see? Correct, it's 2x. So you have 2x, can put square brackets into mu, okay? So we have mu plus sigma squared t, like that. Then plus mu squared, what we have here, plus mu squared, like that, okay? So we can rewrite this as follows. So -1/2 sigma squared, okay? -1/2 sigma squared, you can put the square brackets here, then curl brackets. We have x minus mu plus sigma squared t, like that, this way, okay? So we can square this. When we square that, then we have to subtract this term here. So minus mu plus sigma squared t, like this, okay? Squared, like that. Then you close the square brackets, then you subtract mu squared divided by 2 sigma squared. So the last term here is coming from taking this mu squared outside the brackets. You know, every term here has got this common denominator of 2 sigma squared, and there is a minus here. So when you take the last term outside the brackets, then it becomes minus mu squared by 2 sigma squared. So if you expand this term, okay, you expand this term quadratically, okay, then this term here will cancel with the last term, okay, and that will also retain the original value of this expression. I mean, x minus mu plus sigma squared t squared, what do you get? You have x squared minus, you multiply these two terms, okay, and then you multiply by 2, so 2x, okay, then into, okay, 2x into mu plus sigma squared t, like that, plus the square of the last term, okay, that's mu plus sigma squared t squared, okay. So this term here, this one will cancel with what we have here, and we retain the original value of that expression. So there is no change in value. So that's what we mean. Okay. That's what we mean there. So let's follow so that we see if we can get the MGF of the normal random variable. Okay. So this one is equals to -1/2 sigma squared. Okay. Into x minus mu plus sigma squared t like this. This one all squared plus, we're opening the brackets, okay? So plus, this is a minus times a minus, so it becomes a plus. So plus mu plus sigma squared t like this, okay? Squared divided by 2 sigma squared minus the last term here, which is mu squared by 2 sigma squared, okay? So can we simplify? When you expand this term here, this is mu plus sigma squared t squared. What do we get? Okay, so let's write this. So -1/2 sigma squared into x minus mu plus. So I hope you're following. So mu plus sigma squared t like this. Squared, what we have here, plus we expand this quadratically, okay? So what do we get? Mu squared, that's the first term, isn't it? Are we together?
Yes.
Yeah, we are expanding this term here. So mu squared plus, let's also expand. Let's expand the last term. So you have sigma power 4 t squared, okay? So plus 2 mu, you multiply these two together, then multiply by mu, by 2. So 2 mu sigma squared t, okay? And every term here is over 2 sigma squared divided by 2 sigma squared divided by 2 sigma squared, this common denominator here. So minus mu squared, what we have here, by 2 sigma squared, okay? So the last term here cancels with this one. Are you seeing that? Yes?
Yes.
Then sigma squared here cancels with sigma squared here because sigma power 4 is the same as sigma squared times sigma squared, isn't it? Yes? So we have here sigma power 4. So sigma squared and sigma squared there cancels, so that we remain with sigma squared in the denominator, in the numerator of that term. So this becomes -1/2 sigma squared, okay, into x minus mu plus sigma squared t like this, okay, all squared. So plus what remains is sigma squared here, okay, sigma squared. Then we have t squared over 2, okay, plus sigma squared here in the numerator cancels with this sigma squared, then 2 and 2 cancels. So what do we remain with there? Mu t. Is that correct? Yes? Are you following?
Yes.
Yeah, so that is the simplified form of this term here. Okay, that's the simplified form of this term here. So we can go back here, can come back here and so we put that term inside the function for the PMF. So we move from here this way. So this is equals to the exponent of -infinity to infinity, okay? 1 divided by sigma times the square root of 2 pi, like this, times exponent of, yes? times exponent of negative, what we have here, 1 over 2 sigma squared, okay, x minus mu plus sigma squared t, like this, okay, all squared, so plus, times the exponent of sigma squared t squared over 2 plus mu t, okay? Then the integration is done with respect to x, okay? So we do the integral is with respect to x, so dx, like that. So let me ask you, what's this? What's this up to here? Yes. What is that? Because we can factor outside the integral sign, this term. So exponent of sigma squared t squared over 2 plus mu t times the integral from negative infinity to infinity, 1 divided by sigma square root of 2 pi exponent of negative 1 over 2 sigma squared into x minus mu plus sigma squared t, okay, squared with respect to x. So what is this term inside the integral sign? Yes. Is it easy to see? Is it easy to see? You remember the PDF of the normal distribution, 1 over 2, 2 pi square root sigma exponent of negative 1 over 2 sigma squared into x minus mu squared, okay, with respect to x, like this. I mean, so that's a PDF. So when you integrate this, then it gives us 1, isn't it? Which is no different from what we have here, okay? See, this is the PDF of a normal random variable, okay, with mean mu plus sigma squared t, okay? So when we integrate this, then that will give us 1 as per the properties of PDFs. The integral from the lower limit to the upper limit of PDF with respect to x is equal to 1. So the whole of that term will give us 1 when you integrate. So that is to say that the moment generating function for a normal random variable, okay, is given by exponent of, so mx of t, where x is a normal random variable, is given by exponent of sigma squared t squared over 2, okay, plus mu t. This is the MGF of x, where x has a normal distribution with mean mu, standard deviation sigma. So what we do with this MGF is to differentiate with respect to t, the first and the second times, to give us the variance. Okay. So can you differentiate this term? Yes, class, can you do that? I want you to get the first derivative of this function with respect to t. Okay. When t is equals to 0, that will give us the expected value of x. Then you differentiate twice with respect to t to give us the second derivative of the MGF. Then we can get the variance. Will you do that? Yes? Hello, can you hear me?
Yes, we can try.
Yeah, let me put you in groups of 2 or 3, then you can have a discussion for 5 minutes. Then we come back to the main session. Let me see if I can generate the rooms. Yeah, 8 rooms. Okay, so please join the breakout rooms. Please join the rooms. Otieno, Janice, Abdallah, and Faith. Please join the breakout rooms. If you don't join the breakout rooms, then I'll remove you from this class. Please join breakout rooms. I don't want to see you here. Margaret, Janice, and Omar. Omar, Abdallah, join the breakout room. Otieno, so you guys, you are not even in class in the first place. Margaret, Otieno, join the room or I remove you. Janice.
Charles Mutua. Charles Mutua. Okay, so I think we can now continue. So what did you get as the first derivative? Okay, when t is equals to 0, what did you get? Yes, class, or okay, let me put it this way. The first derivative of the MGF, what did you get? Then when t is equals to 0, yes? So you can just respond at random, anybody can respond.
Excuse me, sir.
Yes.
I'm trying. I don't know if it's correct.
No, but you're just reporting what you got from your groups. No problem. Yes, Antonia.
Okay, so for what I got the power. The one for the exponent was sigma squared t squared divided by 2. Then e, the exponent. Then the power, the same power, sigma squared.
No minus. Sorry.
Yeah, I don't think there was a minus.
Okay, yes.
Then plus mu.
Plus mu.
That's what I got. Yeah, my group got, sorry.
Okay, thank you. So the second derivative, or any other group with anybody with a different solution apart from this? Yes? Anybody with a different solution from this? Thank you, Antonia, for that. Second derivative, another group. You just tell us what you got from your group. Okay, yes, Alan.
Okay, first derivative.
Yes, Alan.
Okay, for us, we were getting, mu squared t.
U squared t.
Over u.
Yes.
No, not over u, over 2. Mu squared t over 2.
Okay, Alan. Over 2, yes.
Plus mu. So close that, all of it into brackets.
Yes.
So that to multiply by the exponent of t.
T.
Okay, yeah. So basically, exponent of sigma squared t squared over 2 plus mu t.
Okay, plus mu t. Okay. Okay. Thank you, Alan. Thank you, Alan, for that. So, any other group with a different solution from these two? Okay, so can
Sir?
a different? Yes.
We got 2t,
Yes, Patel.
2t sigma squared over 2
2t sigma squared
over
over
2
2. Yes.
plus mu.
Plus mu.
Yeah.
Okay, just like that.
Then the whole of the exponential repeated next to it. So it will be exponent, the exponent or exponential of sigma squared t squared over 2 plus mu t.
Like this.
Yeah.
Okay. Thank you, Patel, for your results. So we can also look at the second derivative. Okay. So somebody else to give us the second derivative. Yes. What did you get? We can get three results from 3 different groups. You can raise up your hand if you want to respond. So what about the other groups? I joined a number of groups separately, and there was a very active discussion. How come you are not telling us the results? Yes. Okay. Well, thank you for this. So let's take a look at it together. Let me write down the MGF. Then briefly we write down the correct solution. Okay. I can see one of these responses is closer to the correct answer. So the moment generating function was given by exponent of sigma squared t squared over 2 plus mu t. That was the MGF, isn't it? Yes?
Yes.
Yeah, so we want to differentiate this this term with respect to t, okay? So you can just to simplify, let y, okay? You can say let y be equals to sigma squared t squared over 2 plus mu t, okay? So you want to differentiate y with respect to t like that, okay? So you let y to be the exponent so that the whole term there becomes exponent of y. You understand? Yes?
Yes.
So we are differentiating now, differentiating y with respect to t, okay? So what happens? What do we get here? Sorry, let me write that properly. That is t squared, okay? So first of all, we have 2t here, isn't it? So this power of 2 becomes the coefficient. So you have 2, okay? Then sigma squared, that's a constant, isn't it? Then t, isn't it? The power reduces by 1 when you differentiate, isn't it? So we remain with t to the power of 1. You understand? Yes?
Yes.
Yeah, then divided by 2, these 2 here, okay? So like sigma squared over 2, that's a constant, sigma squared over 2. So when you differentiate t squared with respect to t, you get 2t, okay? So plus, when you differentiate mu t with respect to t, what do you get? You get mu, isn't it? Are we together? Yes?
Yes.
Yeah, so these 2 and these 2 cancels. So we remain with sigma squared t plus mu. That is dy over dt, okay? So then we have, when you differentiate this term here,
That's, you can say x, you differentiate y with respect to x, or x with respect to y, so it remains the same thing. So the first derivative of that MGF will be, so what we have here, okay, that is sigma squared t plus mu, like that, into the exponent of this sigma squared t squared by 2 plus mu t. Okay, that's what we get. That's the correct. So you see, even this one here is correct, given to us by was it Patel? It's only that you do not simplify this, which actually does not change the meaning of the whole term. So this is correct. So when t is equals to 0, okay, like this, the first derivative will give us, so sigma squared times 0 plus mu, okay, times exponent of actually 0 plus 0, because when you multiply any number by 0, you get 0. So sigma squared times 0 is 0. So do you get mu? Yes?
Yes.
Yes.
Yeah, which is the expected value of a normal random variable. That's why we say x, if x is a normal random variable, we say it follows a normal distribution with mean mu. So the mean is mu, which is the expected value of x, and standard deviation sigma. So let's check the second derivative, okay? Can check the second derivative of the MGF. So the first derivative, m prime x of t, is given by mu plus sigma squared t, okay, times exponent of sigma squared t squared over 2 plus mu t. So we differentiate this term once again to get the second derivative. So you can use product rule, y is equals to ab, then y prime is given by a a prime b plus a dot b prime. Okay, so I mean use the product rule. Okay, so we can call this term here up to here, call it a, then up to here, call it b. Okay, so when you differentiate a, you differentiate a with respect to t, what do you get? When you differentiate part A with respect to t, what do you get?
Mu plus sigma squared.
No, but why do you get mu?
Sigma squared.
Yes, correct. Sigma squared, because when you differentiate, mu is a constant. Differentiate with respect to t, you get 0. So mu squared, then we leave b a constant. So exponent of sigma squared, t squared over 2 plus mu t, okay? Plus, we leave a the way it is, that's mu plus sigma squared t, like that. Then we differentiate b. You understand? Yes? Are we together? You leave b, then because we're assuming that y is a product of two terms, a and b. So the derivative of y is given by a prime b plus leave a the way it is, differentiate b. So we are now differentiating this. Are we together?
Yes.
Yes.
When we differentiate this term here, this one with respect to t, then we get mu plus sigma squared t, like this, then exponent of sigma squared t squared over 2 plus mu t, like that. So the second derivative when t is equals to 0 is given by sigma squared. When t is equals to 0, you have exponent of 0 here. The whole of this will reduce to exponent of 0 when t is equals to 0. So that leaves us with sigma squared plus, here we have mu. When t is equals to 0, this term reduces to 0 here. So mu times mu, okay. The whole of this, when t is equals to 0, that will be exponent of 0, which is 1. So we simply get sigma squared plus mu squared. So the variance of a normal random variable x using the MGF technique is given by this formula here. Second derivative when t is equals to 0 minus the square of the first derivative when t is equals to 0. So sigma squared plus mu squared, which is the first term, minus the square of the first derivative when t is equals to 0 from here. So what do we get? Sigma squared, because mu squared and mu squared cancels. Is that correct? Yes. Yeah, that's why we say x, a normal random variable x follows normal distribution with mean mu and standard deviation sigma. So if this is the standard deviation, then it means the variance is the square of the standard deviation sigma squared, which is what we have here. So we've shown how to get the mean and variance of the normal random variable using the MGF technique. So I think that is that. So I think in our next class, we are going to see, we're going to look at the theory of estimation. That's point and confidence interval estimation. So if it's okay with you, allow me to call it a day at that point. I'll share with you these notes so you can form groups and discuss how to solve them. Then I'll supply you with the solutions as and when I do them. That's okay? Is that okay, class? Can we call it a day?
Yes.
Okay. Thank you for your patience and thank you for your participation in class. Have a nice weekend ahead. Thank you.